I am officially. Thank you.
Yes, I was.
Oh, okay.
Right. So welcome to the Simons Institute. My name is Peter Bartlett. I'm the Associate Director. And welcome to the second workshop in the Jumbo program this semester on bridging continuous and discrete optimization. So I want to start with a big thank you to the organisers, Aleksander Mądry, who is the main organiser, Mariam Faisal, Aleksander Mądry, Lorenzo Orecchia, Ben Recht, and Yinyu Ye. And I'll hand over to Ben to introduce the workshop in just a moment, but I wanted to say a few words about logistics. So first of all, we're very proud of the facilities here, and particularly the beautiful auditorium, and we ask you please to not bring tea, coffee, or food inside. You're welcome to bring water, but please leave the rest outside. We've got an overflow room. Doesn't look like we need it right now, but on the far side of the building, 116, there's going to be live streaming to the screen in there of all the talks. So if the auditorium is full during the week, please go over there. As you've seen, we have tea, coffee, snacks. They'll be there in the morning, in the afternoon. Lunches you're on your own, but there's a list of options on the table outside, or you can follow a local or a long-term visitor. There are lockers outside for use at lunchtime also, if you want those. For wireless access, we have, if you have EduRoam from your institution, you can authenticate and use that. Otherwise, there's a Cal Visitor is the open access Wi-Fi network. So all of the talks are going to be live streamed on our YouTube and then archived on our YouTube channel. The videographer, Omid Farr, is here to help. He's also assisting the speakers with hooking up computers. For the chairs of sessions, we're able to take questions remotely via Twitter. So we have a Twitter handle, SIOpt. So if you're chairing a session at question time, it'd be good if you could remind the remote viewers of the possibility of asking questions via Twitter, and the organisers have arranged for that Twitter stream to be monitored. So a big thank you also to the people that did all the local side of things. So Alistair Sinclair, the outgoing Associate Director, who's not here this morning, and the events coordinators, Andrew Jan and Kevin Hung is over here. So if you have any questions about anything, please ask Andrew or Kevin. So now I'll introduce Ben Recht to tell us about the workshop.
All right, I drew the short straw, so I get to give the intro. Welcome. I've been saying throughout this semester that we're talking about bridging the gap between continuous and discrete optimization. And I'm just going to say it again because I like saying it. That I think that the biggest gap in optimization is not between discrete and continuous, but between those who put numerical experiments in their papers and those who don't. And I feel like we have the biggest diversity of folks from both camps today for this workshop. So this will be good. We'll see how many people have plots in their slides. That would be the distinguishing feature here. And so what are we talking about? Like, what algorithms are not iterative? I think that's actually a good question, and hence we have a very heterogeneous group. And at the end of the day, almost everything can be cast in some way as iterative, and that means almost nothing. So let's say, what exactly are we talking about? So I think there are four main themes that we're going to try to cover that are kind of, I think, what we may consider hot topics right now in optimization. Today we'll be talking about using continuous methods for discrete problems, which is something that in the world of theoretical computer science has kind of like we seem to come back to many, many times, right? So now it's, again, I think in particular we'll be talking a lot about interior point methods and fast linear system solves. Our second theme is just on large-scale optimization in general, kind of what the frontiers in that space are. talking about all sorts of new different kinds of ways that we compute and on different kinds of data that we computed on. The third theme is on non-convex optimization, which, or at least iterative methods for non-convex optimization, because non-convex optimization, as we know, is basically everything. So we're going to focus on a very specific case here about iterative schemes that actually can provably solve non-convex problems. And then finally, we're going to have a session on using methods from sketching for optimization. Again, taking now kind of the opposite of today's thing, taking tools from discrete optimization and then applying them back to the continuous world. So starting off the workshop will be, and I guess that this is actually an important thing to say. We're going to have somewhat survey talks kind of to start off every theme. Aleksander is going to give, yeah, exactly, right? I feel like all of us, you kind of signed up for this. So it's Aleksander. Alex, you doing one? I'm going to do one. I think all of us who signed up for this, Fritz, kind of realized that this is actually much harder to do, to survey the current state of affairs than we kind of anticipated, but should keep it entertaining. Finally, we have two special sessions that we're going to try out. One is an open problem session, which will be Wednesday at 4, which will just be a heated discussion amongst all of us, I'm sure. And then second, we're going to have lightning talks, which actually was tried at one of the workshops last semester on machine learning. I thought it was very successful. So we're going to, if you want to give a lightning talk, and I would strongly encourage you, if you're not giving a full talk, please come give a lightning talk. There's lots of cool stuff. Like I'd love to hear about some of the work that Rasmus has been doing lately. So I see something late. Anyway, so if you are interested in giving a lightning talk, email me with a title and put in the subject in all caps lightning talk. And I don't care what else is in the subject. That will be a good filter. So all caps lightning talk. And we're hoping that we're going to preference our fellows and then our long-term participants, but this is open to everyone, so just as space allows. And they're going to be no more than 10 minutes. We might have to make them slightly less than 10 minutes, depending on demand. Okay, so please email me, and we'll send out periodic reminders throughout the day for lightning talk. And my email, right, very easy. Okay, so without further ado, I'm going to hand the floor over to Aleksander.
Okay, welcome everyone. So, as Ben said, what we signed up for was to give you the survey of the field. But then I must say, well, I have to make an admission. So the admission is that I was thinking for a long time what this talk should be about, and I had this kind of vague vision of like I will like survey, how we start from like using convex relaxations to solve like discrete problems. Then we realized that actually you can even solve them, like some of the problems like packing and covering you can solve fast with iterative methods. And then we go with the full circle that now for some of the problems like max flow or matchings, actually the best way to get something done is to cast this as an LP and just solve it fast. Okay, so that was the plan. And then I realized that, yeah, this is much harder to do than it initially feels like. More importantly, I got totally bored. Like essentially, I think at this moment, but given like the mix of like, given that this is what this semester is about, and we have all these experts here, and we had a boot camp, and also we had actually a workshop, and not so far ago, I realized that I would just bore everyone to death, and more importantly myself. So what I decided to do like bait and switch. So essentially, what I want to do, I will talk about something different. So essentially, okay. So what I want to talk about is about our recent result that somehow I think very nicely shows how can you take a problem that is not discrete. It's actually a problem from scientific computing, but you can very nicely view it and like sort of unify the view of this problem by just applying continuous optimization to it. Okay. And somehow, first of all, I really like this result, and and somehow this is a talk I'm not bored to give. So I guess that's something that's one reason for the choice. There's also, unfortunately, much more sad reason for that. So as some of you might know, recently Michael Cohen, who was like a brilliant person, and I would say the spirit of both the theory group at MIT and also of this Simons here. So anyone who have seen it, he was everywhere. He was talking to everyone, and he was like exactly exemplifying this kind of spirit of just learning everything and trying to do everything. And last but not least, my student. So this is actually one of the last works I work with him, and I thought that this would be just fitting to somehow talk a bit about that. Okay, so I'm not sure I'm ready to talk about Michael, but at least I think I can talk about the result he would enjoy, except he wouldn't because he said, okay, we already done it, so why to talk about that? But yeah, so so the way I want to do it, actually, I want to do it on a whiteboard for a variety of reasons. First of all, because I didn't prepare slides, but second of all, actually, I think this is a talk that works better on a whiteboard. So let's just do that. And Ben can punish me later.
For what?
Well, for reneging on the commitment to your.
Oh, just wait till my talk tomorrow.
Okay, that doesn't work well. So I will leave it for a moment, and then we'll talk. Okay. So essentially, this is the result with Michael, myself, Dimitris Tsipras, and Adrian Vladu, and it will appear in this upcoming Fox. And one thing I want to mention is actually there is an independent result by, just so I get the names, all the names right. So Alan Zhu, okay, Lee, Oliveira, sorry, and Vigerson also appears in the upcoming Fox, which is actually very similar in spirit. It gets a bit different bounds, but the spirit is the same. Okay, so what I want to talk about is I want to talk about very classic questions in scientific computing called matrix scaling and matrix balancing. So in matrix balancing, what we are given a matrix A, which is square. Okay, so we are given a square matrix A with all entries non-negative, and then what you want to do is you want to find. So given A, we want to find matrix X, which is a diagonal matrix, okay, such that if I look at the product of X, A, X inverse, okay, so essentially I just multiply. So again, this is a diagonal matrix. It just has one entry on diagonal and zeros everywhere else. Okay. If I look at that, what I would like this matrix to be, I would like it to be balanced. What it means is that if I look at any row of this matrix, okay, and I sum up and I sum up all the entries in it, and I look at the corresponding column of the matrix, and I want to sum up all the entries in there, I would like the sums to be equal to each other. Okay. For every column and every row. So, a concise way of writing this is I would like, so if this will be my matrix M, then I would like M times all ones vector be equal to M transpose times all one vector. Okay? So this is one problem. In a moment I will tell you why you might care for this problem. The other problem that I want to consider is scaling, matrix scaling, in which again you are given an input matrix A, okay, but also you are given two vectors R and C, and what you want is you want to find now not one, but actually two matrices X and Y that are diagonal. Okay, and what you want to do is you want to look at the matrix X A Y. Okay, and what you would like, well, now you would like to essentially look at the corresponding row, and you would like to sum of the row entries to be equal to whatever the vector R is giving you. So essentially, like the ith row should be equal, the sum of the entries in the ith row should be equal to I, and then similar thing is for columns. So essentially, the sum on the sum of the entries in a given column should be equal to this whatever is given by the vector C. Okay, so now these are the two problems. By the way, this might not always be possible. Essentially, it might not be possible for all possible R and C and A. And in particular, one very important special case is exactly the case when these vectors are just all ones vectors, and this just corresponds to scaling the matrix, so it's doubly stochastic. Okay, and similarly here, not always such a balancing exists. Essentially, exists if and only if the corresponding graph is actually strongly connected. But we will not worry about these things at all. Now, a few words. So yeah, these problems were actually quite heavily studied in the scientific computing literature. Actually, algorithms for matrix balancing and matrix scalings are implemented in MATLAB and all the scientific computing software. And somehow, one reason why these are interesting operations to have is that actually they are very nice. They keep very nice invariance with respect to some important scientific computing primitives. So in particular, one nice thing about the relationship between the matrix A and the balanced matrix M is that actually, if we just look at if you just want to get the eigenvalues of the matrix A, if you want to compute the eigenvalues of the matrix A, then this scaling by x and x minus and x inverse does not change the eigenvalues at all. It changes the eigenvectors, but the eigenvalues stay the same. So what is nice about this, essentially, if I have a matrix A that I would like to compute its eigenvalues of, but it doesn't have some properties, like maybe it doesn't have nice properties from the point of view of, from the numerical point of view, you might think of rescaling it to get an equivalent matrix M, which is equivalent for the task that you are actually trying to solve, but it might be nicer here. Okay, and similarly here, scaling actually is nice with respect to solving a linear system in A. Okay, so if this is M. Okay, so essentially, if I have a linear system A, let's call it Z equal B, what I can do is I can, on one hand, just multiply both sides by X from the left. Okay, but then also I can reparameterize Z to make it just Y times some, S. Okay, since Y is a diagonal matrix with positive entries, this reparameterization doesn't lose anything. And now I actually need just to solve a linear system in M. Once I solve the system, I can recover what the solution Z should be very easily. And again, the hope is that the numerical properties of this matrix M actually will end up being nicer than the potential properties of the matrix A. Okay, so this is sort of the theory. Now, the good thing about Berkeley is that even if you get corralled into giving a seminar about some of the results there, then there are some very in the first row there are some very very old professor emerita. And it turns out that actually these are the guys who invented this thing, and then they tell you that actually they don't really want to solve this problem. Like, the reason why they solve this problem is that because they sort of what they care about is the algorithm that solves this problem as opposed to the solution itself. So actually it turns out that all that they wanted a certain property that you get when you, like, a natural algorithm for solving this is applied. And not actually, they never really want to solve this problem itself. So this is how science works, but anyway, that's definitely something something to keep in mind, that somehow you might be, if you are not from the field, you might be mistaken about how much importance there is to actual solution as opposed to some other things. Still, the reason I care about these problems is that, first of all, they actually can be used to compute matchings, which is the thing that I actually care about, and more importantly, I think they lead to a very interesting continuous optimization primitives, and that's what I want to talk about today. Okay. So now, what I will do in the rest of the talk, I will forget about matrix scaling. I will just focus on the matrix balancing, but everything I say essentially transfers over to matrix scaling as well. And as far as I know, this is actually the first time when both of these problems are actually treated in a uniform manner. Usually, there was a line of work on these problems and a line of work on these problems, and that's where stuff. That's how things stood. Okay. Good. So let me talk about this. So what is the idea? So we have this problem. Let's say we want to solve this matrix balancing problem. And now, how do we go about it? Well, I already sort of spoiled the surprise. And, the surprise says that essentially we will try to use continuous optimization to get the solution. Okay? So how can we use continuous optimization to get the solution? Well, there's only one thing that continuous optimization can do. It can just minimize some functions. So essentially what I want to do, I want first to encode this problem of matrix balancing as just a minimization question. like I wanted to correspond to minimizing of some of the of some of the things. Okay. By the way, one thing I should mention is that actually, what are the results that we get? But I will get to it later on. I also did not discuss, as you notice, the previous work, which actually is quite extensive. So let me just say that the current best known algorithms for the problem is that for matrix scaling, it's just roughly n to the 4. Like if I want to get like epsilon close approximation to the problem, then actually I have to spend time that is roughly n to the 4th, and this is a result due to Kalantari and Hessian, I think. Kalantari, Hessian. Okay, from 96. Okay, for matrix balancing, there's actually a couple of relevant works. So there is actually Schulman and Sinclair. Sinclair had one result. It's in 2015, and they got the running time of n cube log 1 over epsilon. And then also recently, there was a very nice work that actually inspired us to look at this problem by Ostrowski, Rabani, and Józefi, and this is 17, which essentially showed algorithms that are actually nearly linear, except they depend polynomially on 1 over epsilon as opposed to logarithmically. So they get a time of like something like m plus epsilon. Okay, so that's all I would say about this work. And what we get actually is, what we get is actually we get the time that is roughly m times log of q, like k of x star, log, well, so just essentially this is just like the bit complexity of the problem. So essentially what they are essentially linear, like the running time is linear times the log of the what I call the condition number of the optimal matrix X. So essentially, like if X star is the optimal solution that actually gives exact balancing, I want to look at its condition number, namely the essentially ratio of the largest to the smallest entry here, because it's a diagonal matrix. So essentially, we depend logarithmically on that, and we just add linear, like the linear time on top of it. Okay, so this might sound like something being small, except it actually isn't. So unfortunately, the condition numbers of this optimal solution may be even exponential. So essentially, this just, in the worst case, it's never more than n. So essentially, in the worst case, this is the running time is mn log 1 over epsilon. But so for special cases, for instance, in the case where the matrix A has all the entries positive, it's actually, this thing is logarithmic. So essentially, then you can near linear time. Okay? So these are the result. Yes?
I thought the Schulman-Sinclair result was for the L-infinity version of the problem.
Yes, but yes, so essentially it was, except, sorry? It's a bit harder. Okay, I didn't want to get into that. I think when you have logarithmic, like essentially, okay, for L-infinity it's not exactly true, but, for any LP things, this doesn't matter, except for L-infinity, which, I just, okay. Again, problem with experts in the audience that actually they know what I'm talking about and they can call me out. Like the point is that yes, this is a bit harder version of the problem. They are all essentially equivalent. Like I think I think as long as you are in the regime of log 1 over epsilon. Here, when you are in the regime of polynomial epsilon, this is actually you have to be very careful how you define your error. But in the general regime, it doesn't matter that much.
Do you have bad examples where the log of this?
Yes, we have bad examples when the log. I will talk about that. Yes, so essentially, it's actually this bound is essentially tight for our approach. Okay, it doesn't mean that it is it is optimal. It just I will explain exactly. There is a very good way of explaining what are the limits of our approach. Okay, so essentially, so all we need now is just to set up a function that actually captures, like minimization of which captures what we want to do, and the function actually is very easy. So essentially, so the way I will work now is I will just reparameterize the problem, and I will think that my matrix actually is, well, the rebalance matrix corresponds to, like, I don't keep exactly the matrix X. I actually keep just, the logarithms of the entries. Okay, so this is like X to minus X, essentially. So my, like, each entry is just like, X now. Okay, so maybe I should change it. Maybe I should call it y.
This is very tiny.
Sorry?
This is very tiny.
Sorry. So essentially, what I have is that my, like I want still tiny. Okay, good. So that's great. Good. So essentially, I want just my matrix A, my balancing matrix, to correspond to exp to the y. Okay, so essentially, I'm just keeping, it will just make all the expression easier if I think about the logarithm of them as opposed to so then directly. And then the function that I'm trying to minimize is just the sum over all entries, the ij entry times e to yi minus yj. Okay, so this is the function I just want to minimize, and I claim that minimizing this function corresponds to solving the balancing problem. Why? Well, in continuous optimization, there is only one reason why, and the reason is just to look at the gradient of this function. Okay, and when you look at the gradient of this function, what you will realize that very conveniently, that essentially, it corresponds to just the difference of two vectors, like Rm and Cm, when Rm is just the row sums of this rescaled matrix. So this is like exp y a x minus y. Okay, and C are the column sums. Okay, so clearly this is 0. If this is 0, this immediately implies that the column sums are equal to the row sum. So clearly, this indeed will mean that the matrix is balanced. Okay. So far, so good.
Did you say that the A's were not negative or not?
Sorry? Yeah, the A's are non-negative. Otherwise, I would be in a world of trouble. Right? Because exactly, if you look at this function, so clearly finding a critical point of this function gives you the solution. Now the question is, how do you minimize this function? In particular, what I'm sure Pablo was worried about is that if these entries are not non-negative, this function is not convex, and then we are in the non-convex optimization regime, and Ben did not let us get there yet. So essentially, yeah, we are assuming here that all the entries are non-negative, so this function is convex, and then essentially we know that in principle we can, by applying gradient descent, we can eventually get to a good solution. Okay, and in a sense, the result of Ostrowski, Rabani, and Józefi can be viewed as a gradient descent scheme applied to a function like that. Okay. However, we want to get logarithmic dependence on our epsilon, so just applying gradient descent to this and just like waiting for it to converge might not be like, it does not give us fast enough convergence. So, you would like to use some stronger tool to actually minimize this function. And what is the stronger tool in continuous optimization that you usually use in such cases? Well, essentially when you don't have strong convexity, which in principle you don't have here, well, what you do is essentially use second order methods. Okay? So essentially you use Newton method. So what does Newton's method correspond to? Essentially, the way Newton's method works is that it looks at the approximation of the function around a given point, and actually looks at not only at the Taylor approximation. So this is f of y plus the gradient of f at y times delta. So this is like the first order approximation, but it actually looks at also at the second order approximation of this function, which involves the Hessian of this function. Okay. And then there are further terms. And what it says, okay, I will view my function as this, as this just quadratic approximation, and I will just try to directly minimize this. So I will try to go in the direction of that corresponds to minimizing this quadratic proxy for my function. Okay. So when you work it out, the direction that you actually will end up going is, the delta Newton is essentially minus the inverse of the Hessian times the gradient. Okay, and that's how the Newton's methods work. Now, if you remember from the bootcamp, you realize that one thing about Newton's method is that clearly its convergence you would expect to be superior to the convergence of the gradient schemes because it's using better approximation, except there is a problem because actually, the problem is that somehow we might be overfitting to this local approximation of the function. So essentially, Newton's method works only well, works well only if what happens is that essentially we only use it in the neighborhood of y, in which the Hessian does not change too much. Okay, so essentially Newton's method is good. It's good only as long as whatever point y prime we go to, okay, well, the Hessian at that point is roughly similar to the Hessian at the point we started with. Okay, somehow only then we can actually say something intelligent about how good the approximation is and how much progress we make. Okay, and the usual struggle when applying Newton's method is exactly figuring out what is this neighborhood of where the Hessian actually would work. Okay, so and that's exactly the question that will motivate our algorithm here. Okay, so we now already know what is the function that we want to minimize. We know what is its gradient. So now let's take a look at what is its Hessian. So the Hessian of this function is actually something very simple. It's essentially the diagonal matrix that you get by taking the vectors corresponding to the row sums and the column sums and just like making a diagonal matrix out of it. And then you subtract from this. A matrix M plus M transpose. Okay, this is the Hessian. Okay, so so now we have one of the Hessian, and now we can try to understand. How quickly it changes as we actually vary y. Okay, essentially, if I fix, if I take a snapshot of the Hessian at y, and then I start moving, the question is, how quickly does the corresponding matrix actually become very different to the matrix I started with? Okay, and when you think about it for a moment, then what you will realize that essentially, the one sufficient condition is that, as long as my new point y prime is at most 1/2 away in L infinity norm, so essentially as long as I didn't change any of these individual entries by more than 1/2, then essentially what happens is then what happens is that the corresponding entry xi, which is e to the yi, is essentially multiplicatively approximated, is with a multiplicative error of 1/2 of the new entry, which is xi prime, and this turns out to be sufficient to essentially show that these two Hessians are actually close. Okay. So essentially, the key insight here just says is that I can, if I want to minimize my function f by looking at this quadratic approximation and trying to go in direction in which this approximation tells me, then this will work as long as I will never move more than 1/2 in L infinity norm away from the point where I started. Okay? So essentially in this radius, like in this, if this is my function, if this is my point y, then there is this box of radius 1 around my point, and essentially as long as I just minimize the function in this box, and as long as I will find the minimizer of this function in this box, then I can actually quantify how much progress I make. Okay? Once I'm outside of this box, essentially this approximation, like we lose any control over this approximation and we don't know what happens. But as long as we just minimize it inside this box, we are fine. We are making progress. Okay? So what it motivates is, this exactly motivates the algorithm for solving of this problem. So how does this algorithm work? Well, essentially what we do is exactly what I said. So we just start with some initial point. Right. We just start from some initial point, y0, okay? And now in each, for each I from 1 up to however long we want to run this procedure, yes?
Is the infinity bound constant? Is it a half or half of y or y prime?
No, it's half. It's just half. It's really actually half. Because like essentially remember that y's are exponents in essentially xi's are just exponents of y. So as long as I just add up to plus minus 1/2, this will change by at most a factor of 2, one way or the other. And that's just enough to get the statement that this this new Hessian is actually within a like spectrally approximated by the old Hessian up to a factor of 2 as well. Okay. Good. So what is the algorithm now? Well, what we do is that essentially we to get our point like I plus 1, get point yi, what we do is essentially we just find a minimizer. So this is argmin over all y's prime such that they are in this box around the previous solution. Okay, so essentially we ensure that we only look around the solutions that are within 1/2 in L infinity norm from the point where we started of this quadratic approximation here. Okay, let's call it fy of y prime. Okay, so essentially fy of y. Okay, so essentially what we are doing is essentially we are always, we look at the current point, we look at its local quadratic approximation around this point, and then we find the minimizer of this quadratic approximation subject to staying in this box around our initial point. Okay, so just for the record, this is not how the original Newton's method works, because the original Newton's method just cares about L2 and essentially it just always moves in the direction. Here, there is in general no closed form solution for this problem. Okay, this is just some optimization problem that we have to solve, and we just call this primitive a box constraint Newton's method. And now we just want to apply it to our function. So clearly, again, we don't go to analysis, but this is not hard. It's just saying that each time we maintain this condition, as long as we stay in the box, this actually makes a lot of progress. Like essentially, you can quantify how much progress you always are guaranteed to make. So essentially, the theorem that you get out of this is that you can, this method will converge to an epsilon approximate solution in the number of iterations. That is at most, O of, log 1 over epsilon, or the bit complexity of the problem over epsilon. Now, but there is a quantifier here, and essentially this is at most R infinity, where R infinity is just the radius of the problem in L infinity norm. So essentially R infinity is just, okay. So I'm lying a bit now, but I will explain how I'm lying in a moment. So this is essentially the L infinity distance of my initial point and the optimal point. Okay? So notice, by the way, okay, so the way I'm lying that actually you don't only need to bound this radius for the initial point, you actually need to bound it over the level set in which the initial point lies. But let's just not worry about this. You just have to do some extra work to go around it. But this is the heart of it. But the important part is that actually this shows that actually this bound is essentially close to optimal for this setting. Why? Well, because notice that in each step we always insist by moving by at most 1/2 in L infinity norm. So just to get from y0 to whatever y star is, I just need to spend this many steps roughly. Okay, and then we are just adding, a logarithm of 1 over epsilon. On top of that, we can really converge to this close to optimal solution. Okay, so this is the statement, and it looks like we are almost done, except we are not. Okay, because this gives an algorithm, but then there is one thing that is still missing. Essentially, we don't know how to solve this optimization problem. It's like in each iteration, we have to solve this optimization problem. Okay. So, let's look at what this optimization problem is. Well, essentially, this optimization problem corresponds to minimizing a quadratic function, yes, because it's a quadratic function, over a box, right? So, essentially, in the end, the primitive that the thing that we need to solve is essentially minimize over some z that is supposed to lie in a unit L infinity box. And what we want to minimize is a function which is just a, let's call it bz plus some little b times z. So essentially we are trying to minimize an arbitrary quadratic function with b being non-negative, like all entries non-negative, over a box. Okay? So the funny thing is, how to do it quickly. So first of all, notice that if I didn't have this constraint, okay, then actually essentially I would just minimize over z this quadratic form, then we exactly know how to solve this problem. This problem is equivalent to just solving a linear system in a linear system in the capital B. Okay, that's exactly what the solution is. Okay, in particular, that's how you actually solve these systems in practice. So that's good because actually, the matrix we are using here is actually the Hessian of our function. And as I conveniently erased now, but if you look at the Hessian, it turns out that not only it's actually a like positive semi-definite, so the function is convex, but actually it's also an SDD matrix. Essentially, it's just essentially just symmetric diagonally dominant matrix. And what it says is that actually for SDD matrices, we know how to solve such linear systems very, very efficiently. So we can actually do it in nonlinear time. Okay? So that's great, because now we have all the machinery for solving this linear system, except what we are doing here is more general than that, because we also have these constraints. And now it's no longer just like a solving a linear system. So somehow it could be solving a linear system as long as we optimal solution never violates these constraints, but in general this might not be the case. So somehow we have to take into advantage these L infinity constraints. So, long story short, what we say is that actually still, even though this is a generalization of the kind of SDD solving, we can leave the tools of the approaches of SDD solving to the setting. In particular, the solver that we use is the solver due to Lee, Peng, and Spielman from 60, which basically it works very nicely. Just essentially what it does, it just looks at the matrix, it iteratively figures out sort of the submatrices of this big matrix that are easy to solve. It just solves them recursively and then uses Schur complement to recurse on the rest. Okay, and it turns out that even though this was something designed just for solving the problem without this thing, it essentially solves this problem as well. Okay, so technically what happens is we get a solution that violates this bound, this bound of radius 1, but violates it at most by a factor of logarithmic, which is completely fine with us. We just take a smaller step size, and essentially we just get another factor of log n in the running time, and everything works.
Do you pay price in complexity for using a two-norm ball instead of an infinity norm ball?
Sorry?
If you were to use a two-norm ball, like inscribed in an infinity norm ball, does it make the complexity a lot worse?
But meaning, sorry, for which problem? For this problem, or for the subproblem? Then it's actually I think just like solving. It's just really solving linear system, right? Is it? No, it's not. Yeah, it's not.
The point is that's a much easier problem to solve.
Sorry?
If you have a two-norm ball, the subproblem is much easier to solve.
Yes, I would suspect, but it's not helpful for us.
Well, tell me why it's not helpful. That's why I asked the question.
Yeah, so it's not helpful because essentially, okay, I guess. Well, so the point is that L infinity, taking a step in the unit. Well, L infinity box is actually much larger than L2 ball, and as far as I remember, again, I will not. Dimitris, do you know? My intuition is I would need to check it. Thing is that actually when you are constrained to only take steps in L2 ball, you will actually need many more steps to converge. Essentially, the L2 radius will be much larger than the L infinity radius.
Well, I just make the point though that the L2 problem is much easier to solve, and you could still use SDD there because you just have to add it.
Yeah, well, so essentially, so you just add, the Lagrange multiplier for that, and that everything is nice. Yeah, so I know that it's easier, except we really need L infinity here. Yeah, so when I said that this is solving is just we just add Lagrangian term, and it's still solving a linear system.
Yeah, so the radius of the ball becomes square root m times larger, right?
Yeah. Okay. So of course, yes. So definitely, like always, we know that the L infinity radius is it's at most like square root of m smaller. So this is definitely like, so by doing what you propose, we in the worst case lose square root of m. Except I have a feeling, I'm pretty sure, like there are examples where actually you really pay the square root of m. Essentially, this you really like pay for this worst performance. So if you can get the same thing for this L infinity bounded problem, that's what you want to get. Okay. And somehow, yeah. And as you see, this actually like generalizes. So essentially, like the only thing we really needed from the function f is essentially that like for this general approach to work is that this this function has this property that the Hessian is stable as long as we move by 1 in L infinity norm.
And you're not going to pay that square root of m price in solving the subproblem, by having to solve a whole bunch more STDs here and there.
No. So the point is that actually you can solve this problem with just logarithmic number of SDD calls. Okay, so this is not obvious, and you have to work for it. But in the end, like this particular solver is particularly nice for that. That actually you can adjust it and get the right thing. Okay, because like somehow the point here is that this thing always works with like a very well conditioned problem, and then just enforcing this infinity constraints there is sort of easy. Okay. But yes, this is not obvious that this is, essentially you can get it at the same price tag as just if there was L2 bounded.
Okay. The last comment.
Yeah.
What if you use a scaled L2 ball like an ellipsoid?
That's a great question. I don't know. That's a good, again, you can definitely, in principle, you can approximate, what you need from this L infinity ball by ellipsoid. So possibly this could be something that works, but we didn't try it. Okay, and I will just, if I will have time, I will just touch briefly about, what is the barrier here? And this might also answer this question. Okay, so essentially that's almost it. I just described to you all the main ingredients of the algorithm. What I want to finish with is actually I want to give you a bit different perspective at the problem that we are solving here. Okay, so essentially so far we just thought about we are trying to find this matrix balancing. And then this corresponds to minimizing this function. But there's actually a very nice, and somehow to solve it efficiently, we need to use this generalization of the SDD systems, like of the SDD system solving. So it turns out that there is some very nice kind of way of looking at the problem that somehow makes a nice analogy of what happened in the context of electrical flows and the importance of SDD solving there. So essentially, what happens is that actually you can view, like instead of looking at the matrix balancing or minimizing of this function, you can view just look at the problem that I will call nonlinear flow problem. Okay. So think of it as a generalization of the electrical flow problem, in which in electrical flow problem, I just give you demands, right? And then I want you to find, voltages that, induce an electrical flow via Ohm's law that satisfies these demands, right? That's what electrical flow problem is. And we know that essentially this corresponds to just solving Laplacian, voltages correspond to just solving a linear system in the Laplacian. Okay? That's exactly what the electrical flow problem is. So this is the electrical. Okay? Now, what we want to consider is, so here electrical flow, the crucial thing here is that just the Ohm's law, okay, which says that essentially my flow induced on the edge ij is exactly given by the difference of the potentials between between I and j, well, divided by the resistance. Okay, this is how we go from the voltage space to the flow space in the electrical flow question. Okay, and then we know that if you want to find the right voltage that induce the flow of demand d, that's what we need to do. Now imagine a generalization of this, which I call exponential Ohm's law. Okay, which the flow that you actually get on the edge ij is not just linear in the differences, it's actually exponential in the difference. Okay, so it's just equal to, let's call it 1 over rij of exponentiation of xi minus xj. Okay, this is still a well-defined problem in which I want you to find voltages xi and xj such that if I look at the flow induced by this by these voltages according to the exponential Ohm's law, I want to satisfy the demands. Okay, so essentially you can view that there is some operator like L that takes the voltages and gives you the flows, and you would like it to be exactly, satisfy the demands that you wanted. Okay. Well, the problem here is that now this operator is no longer linear; it's exponential, and the question is, how do you solve such a question? Well, it turns out that solving the balancing problem is exactly essentially equivalent to this question. Okay, so essentially that if I want to solve a balancing problem, then okay, so essentially like the balancing problem corresponds to essentially solving this equation Lx equal all zero. So you just want to find a flow that has zero demands. Okay, in which your resistance 1 over resistance is exactly equal to the corresponding entry in your matrix. So essentially you think of your matrix as specifying a graph with resistances, and then you want to find the flow that has zero demands with respect to this exponential Ohm's law as opposed to linear Ohm's law. Notice that like for linear Ohm's law, if I want demands to be zero, then the answer 0 is always correct. Here actually it's actually quite non-trivial to compute it. You actually need to to use this algorithmic machinery to just solve that. But I think this is like a very nice nice analogy to what happened to electrical flows. With electrical flows, they correspond to the linear Ohm's law, and then solving SDD systems becomes like the crucial primitive to just solve it. Otherwise, here for the exponential Ohm's law, this corresponds to matrix balancing, and also you can encode matrix scaling in it as well. And then the primitive that becomes is still an SDD solver, except now you have to solve this more general version of it. Okay. So the last thing I just want to say is that the bands that we had here, the question is are these bands optimal? Well, clearly they are optimal for our approach because the way we bound things, you never can move by more than 1/2 in L infinity norm. So you always will have this barrier of this L infinity barrier of this L infinity radius. Except what we do feel is that this is answering to your question initially that actually there should be a way, like somehow, clearly. As long as you never move more by 1/2 in an infinity norm, you will be safe. Like your approximation, quadratic approximation of the function will always be good. But maybe you can sometimes move much further and still have control over how this approximation happens. So I think there is something to understand here. We don't have a good idea how to extend it, but essentially this would be the frontier of it that I find very interesting, and I would love to talk to you if you are interested. Okay, thank you.
Back to the theme of continuous methods for discrete optimization. Is there anything discrete here?
No, nothing. I cheated. I'm sorry for wasting your time.
Is it related to anything discrete?
Well, you can encode computing matchings in it. So this is the connection. But honestly, like this is just this is not I wouldn't say this is a very compelling connection here.
What's the connection with synchron balancing in this?
Well, synchron balancing essentially is is just a way to solve scaling problem, in which just like gridly. Essentially, what you do is essentially you. What do you do exactly? You just. Yes, exactly. Yes. So essentially, you either just want to update things so you just get the columns right, but this can break rows, and then you do rows. This can be columns. So essentially, I think you can. So I didn't verify it, but my feeling would be that the synchron balancing would correspond to just a gradient descent scheme on this function.
What's the runtime of synchron?
I don't know. That's a great question. I don't know.
It's a very simple method.
Yeah, it's a very simple method, and essentially it corresponds. So what I do know is that the Osborne iteration for matrix balancing can, like with the right pivoting rule, can be viewed as just a natural gradient descent on this thing, on the corresponding function. So I suspect that something similar is true for synchron balancing, but I cannot say.
More like alternating minimization.
Sorry?
Alternating minimization.
Maybe. Okay. Yeah, you're probably right. Yes.
So you're using convexity of f, but actually something stronger is true, right? That the log of f is convex.
Yes.
So somehow doesn't that? I mean that's at least a classical way that one would approach this kind of thing, right?
Yeah.
Because you still have that the Hessian is diagonally dominant, and then you can do.
Yeah, that's a great question. I don't know. I think we thought about it briefly. We couldn't get anything out of it really. But yeah, it doesn't mean that there is nothing there.
Yeah, so Michael knew how to use the log of the functions convex to improve something.
But like nothing better than we had, right?
Not truly better, not some log, so log W or something.
Talk to Michael.
Is there any argument against being able to solve the subproblem very exactly in your linear time? And the case would be as STD.
I don't see any reason why you shouldn't be able to do it. We just don't seem to get any mileage out of it, so we didn't really try. So.
Thanks.
Yeah, like it's actually interesting, what kind of generalization of this, like because this is generalization of Laplacian solving of SDD solving. So, question is, how far can you push it, and like what interesting can you find here?
Just a nice.
Okay. Thank you.